Hi everyone, and thanks all for attending our newest IYCN Science Café. So for this month's cafe, we'll be talking about nanozymes, and we are happy to have with us Professor Vincent to accept our invitation. So beginning, I will introduce myself. My name is Rotello. I am the IYCN Conference President's Committee Co-Chair, together with my colleague Tracy. Tracy, would you like to introduce yourself?
Hi everyone, my name is Tracy Lau and I am the IYCN Conference President's Committee Co-Chair as well.
Okay.
I'll pass it back to Wally.
Okay, so we'll have together with us our colleague also, Elisa, who will be with us in the background. So beginning, I will give a brief introduction about who we are, and then followed by a 30-minute presentation, which will be given by Professor Vincent, and then a Q&A session and 5 minutes for closing remark. So beginning with who we are, who are we? We are the International Younger Chemists Network, the IYCN, from 2017, and we have been associated to the IUPAC. Our vision is to connect and empower younger chemists globally, and also we have a global mission to support and advocate younger scientists working in the chemistry, in the chemical sciences toward a globally sustainable future. So if anyone is interested in joining us, please head to the membership form. As you see it, www.iycnglobal.com/membership. And also the membership is for free, so feel free to apply with us and join us. Also, if you want to connect with us, you feel free to either send an email to us or to connect us through various social media platforms, through LinkedIn, Facebook, Twitter or X now, and Instagram. So moving further, I would like to thank Professor Vincent for accepting our invitation. And here I will be giving a brief introduction about who is Professor Vincent. Professor Vincent is the Charles Gozman Professor of Chemistry and distinguished professor at the University of Massachusetts. He received his bachelor's in chemistry in 1985 from Illinois Institute of Technology and his PhD in 1990 in chemistry from Yale University. He is an NSF postdoctoral fellow at the Massachusetts Institute of Technology from 1990 to 1993. He received several prestigious international awards and national throughout his career. The most recent one is the highly cited researcher by Thomson's Reuters Clarivate and the Arthur Cope Scholar Award in 2023. His research program focuses on synthetic organic chemistry to engineer the interface between synthetic and biological worlds and span the areas of devices, polymers, nanotechnology, and bio-nanotechnology, with more than over 600 peer-reviewed published papers till now. Without further ado, Professor Vincent, the floor is yours.
Thank you. Let's see, so there I am. Okay, I want to start out by thanking the organizers for inviting me. There is something impressive about and really heartwarming about being invited by a bunch of younger scientists. You know, being a father and having a teenage son, when the young folks look, it's good that they're paying attention. So with that, I'd like to talk to you about sort of a specific brand of nanozymes. There's a lot of nanozymes out there. We're sort of this small area of nanozymes focusing on bioorthogonal nanozymes. And our goal for this is to basically harness transition metal catalysis to generate therapeutics. I'm going to be talking about 3 different areas today. I'll be talking about how we can use the protein corona to control catalysis, how we can control intra versus extracellular catalysis, and finally, I'm going to take you to some in vivo work where we do in situ drug generation at tumors. So, bioorthogonal chemistry, what is that? Well, a lot of folks, you probably all know. I mean, it was the topic of a Nobel Prize a year and a half ago or so. But the idea is doing chemistry that nature can't or won't do. In other words, chemistry that biological systems cannot do. So if you put something in that doesn't react under biological conditions, we can very often cause it to react using the tools of chemistry. So if you look at my background, I started off as a synthetic organic chemist. What we're doing is using the power of synthetic organic chemistry to do things that nature can't. So this opens new doorways for research. So that's great. And there's been a lot of work, for example, on click reactions and various sorts of glycan modifications. Let's take it a step further. Let's look at bioorthogonal catalysis. If we have a catalyst, we can do a lot of chemistry. A single catalyst can do many transformations. And what it provides is it provides the potential for on-demand factories for active agents. And this can be used, for example, as you can see on the right side, to convert a profluorophore to a fluorophore or a prodrug to a drug. And this is the idea, if you think about it. If you have a bioorthogonal catalyst, you can take an inactive species that you have over on the left, convert it through catalysis into an active species. So I'm going to start off talking about gold nanoparticles, and we've been doing gold nanoparticles, I'm guessing longer than most of you folks have been alive. We started them somewhere in the late 90s. And question that we had back then, this is a slide that's over 20 years old. The questions are still relevant. Why do we want to use gold nanoparticles for biomedical use? And one of the reasons is that gold has low toxicity. If you take a look at Ayurvedic medicine in India, Ayurvedic medical medicine practitioners will drink colloidal gold, and they will drink enough colloidal gold to turn themselves purple. There hasn't been any demonstrated health benefits from turning yourself purple, but there has not been any negative consequences. So you can basically take all the gold you want and it won't be harmful. Reasonable clearance, what does that mean? Well, basically gold particles, if they're small, can be cleared directly through the kidney. If they're not cleared directly, what will happen is gold will slowly oxidize from gold 0, the metallic gold of the nanoparticle, to gold 1. And then the gold 1 particles will hitchhike onto serum albumin and they'll be excreted. So those folks that are taking the liquid, the colloidal gold, they will turn normal colored in a period of weeks to months. The thing that we really like about these particles is that they are beautiful platforms for presentation of functionality, because what you can do is you can take a simple nanoparticle, the one that you have in the center here. I'm not going to risk doing the laser pointer thing because that can get risky. But anyway, you take the scaffold we have in the center, and you can do what's called the place exchange reaction. Any thiol can add to the surface of this particle, kick off the thiols that are on the surface, and with that, you can generate in one step reproducible, scalable particles. Now, we have a particular particle we like, and that is the 2 nanometer gold core. And a bit of history here. When we started doing the gold nanoparticle work, what we found was that it was really easy for us to bind proteins, because what we could do is we could take, we could basically take a, I'm going to give it a try, see what happens. We could take a simple alkane thiol with a charged N group, and this would bind electrostatically to proteins. But what we found that it denatured those proteins, which can be useful because the denaturation can be something that can be applied biologically. But what we really wanted to be able to do was control how these particles interacted with proteins. So what we did is we took the scaffold, and then we put on a tetraethylene glycol layer. And what we found when we did that, we got totally inactive nanoparticles. So in other words, they did not bind to proteins at all. They basically behaved like high molecular weight PEG. What we found is that when we then put the charged groups on the outside of these monolayers, we had protein binding. And not only did we have no denaturation, but we actually had stabilization. So key thing here is that the core size is important. If you have a small core, then you get a radial structure on your monolayer. That radial structure allows the oligoethylene glycols to become hydrated and separated and non-interacting. The particles are a lot of fun to work with. They're stable in serum. They're lyophilized. So we lyophilize them and we ship them all over the world. So they're useful. Now, let's take a look at using the corona to control nanozyme activity. So let's first think about what the heck we're going to do for the nanozyme. First thing we're going to do is we're going to take a gold nanoparticle with this monolayer. And if you go back here, what you'll notice is that you've got these three distinct layers. You've got the charges on the surface, you've got the oligoethylene glycol layer, and then in the interior, you have this hydrophobic region. That hydrophobic region is a great place to bind metal catalysts. So what we can do is we can quite simply put metal catalysts in with these gold nanoparticles. They'll work their way into the hydrophobic interior, and then we can generate these nanozymes. And these are bioorthogonal nanozymes. I'll show you the catalyst in a minute, but the basic idea here is that we have two different particle surfaces. We have this particle surface here that's designed to bind proteins and denature them because it's just an alkane thiol. And then we have this monolayer that's designed to bind proteins reversibly. So what our hypothesis is that if you bind proteins to the surface of the particle and they denature, you're going to generate basically this protein coating or this impenetrable protein coating around the nanozyme, and it will become inactive. The particle that has the reversible binding should still have activity because the proteins will pop on and off. Now, what happens when these particles go into cells? Inside the cells, cells will take up nanoparticles through an endocytosis process. Endosomes have proteases. So the idea here is that the particles get endocytosed, proteases will chew off that denatured protein around the outside, activating the nanozyme. And for the one that's at the reversible binding, you should maybe get a little bit of acceleration because you'll have fewer proteins around. So that's great. So how do we make these catalysts? Well, what we do is we take this ruthenium catalyst. You can see it's nice and hydrophobic. Incorporate that into the gold nanoparticle monolayer. And what we use to activate initially is this fluorescein derivative, or rhodamine derivative that has allyl groups. Now you look at that; these allyl carbamates are not cleavable by biological systems. There's no carbaminate enzymes out there. There's no allylase enzymes. So this is truly a bioorthogonal reaction. So if you take a look over here, see, I need to move the panels because I can't even see my screen. If you take a look at the particle with the, let's see, this is the one. Okay. Okay, so this is the particle that has the monolayer that denatures proteins. And what you can see is that if you have the nanozyme 1 with the protein, so in other words, the corona and the nanozyme 1, there's no catalysis. So you do not see any catalysis. If you put in trypsin, you see catalysis. So what's happening is trypsin is basically chewing up the monolayer, generating the free catalyst. If you look at the nanozyme that doesn't form the corona, what you see fast catalysis. If you put it in trypsin, you see slightly faster catalysis. And then the inhibitor brings it back to where it was. And if you look down here, you can see, look down in the right-hand corner, you can see very clearly the nanozyme 1 is only active with trypsin, trypsin, and not with the trypsin inhibitor, whereas nanozyme 2, the one that has a reversible binding, is active all the time. So what do we have here? Okay, let's take a look at what happens when we put them in cells. Well, if we have the one that denatures, we see that we get good fluorescence generation inside the cell. And that's because the particle's being taken up with the corona on it, and the corona is being shooed off. If we put a protease inhibitor in with the cells, we see no catalysis. Saying once again that if you don't chew off the proteins, you don't get activation. Nanozyme 2, that one is active without the inhibitor. With the inhibitor, it's slightly less active. The prorotamine, just the perfluorophore, no effect. And so we can generate a dye. What about a therapeutic? Okay, well, we don't have a therapeutic activation. So now let's take a look at what happens when we do controlling the enzyme localization using surface chemistry. Now, this is one of the things that we're really interested in as a group. And the idea is this R group here can be used to dictate where things go. And so if you have a gold nanoparticle that has a positive charge, it will interact rapidly with negatively charged cell membranes and be endocytosed. If you have a zwitterion, in other words, it's a system that's charged but overall neutral, these systems tend to be very inert biologically. They don't bind to cells, proteins, etc. If you have that, you should have a system that stays outside the cell. So here's what we want to do. We have a cell permeable dye, pro dye, which is this, once again, this prorotamine derivative. And we have a cell impermeable dye, which is an allylated resolution. And so if you take a look at your catalysis, what you find is that if you take the positive nanozyme with this perfluorophore, you see good fluorescence. You see the positive one with this perfluorophore, you see good fluorescence. You take the zwitterion with either of these, you see good fluorescence. None of the controls show any fluorescence. So the dyes themselves are not fluorescent. So let's take a look at what happens when you put these particles in with cells. If you look at the plots, what you have on these plots is uptake of gold on the y-axis and then concentration of the different nanozymes on the x-axis. Technique we use is inductively coupled plasma mass spectrometry. And what happens with that is you basically take your analyte, you dissociate it into solution, and then you blast it into individual ions in the plasma. So it's a beautiful system for tracking metals because there's very little gold and very little ruthenium in cells naturally. So they're going to be really easy to track. So you take a look, what you see is with positive nanozyme, if you look at uptake, you see that as you increase the amount of nanozyme, you see an increase in uptake of the red, which is the gold, and the blue, which is the ruthenium, meaning they're both going in together, which is good. If you look at the zwitterion, you see very little cell uptake. And this is true in HeLa cells, which are cervix cells, or Ra264.7, which are macrophage cells. In both cases, you see very little uptake of the zwitterion, lots of uptake of the cation. And so what you get here is a really complicated slide where you can see that you get catalysis where you want it. So in this case, what we have is the nuclear stained is blue. The perfluorophore 1 is green. Perfluorophore 2 is red. So if you look at the far left panel, what you see is if you have just the pro dye, no catalysis. That makes sense because the cell has no mechanism for converting the pro dyes to dyes. If you take the perfluorophore 1 that goes into cells, and you put in the positively charged nanozyme that goes into cells, what you see is you see brilliant green fluorescence inside the cells, meaning you're getting catalysis inside the cells. If you take that sphitterion nanozyme that doesn't go into cells, and you put it in with a profluorophore that doesn't go into cells, what you see is lots of red fluorescence outside the cells. Particle doesn't go in, the nanozyme doesn't go in, the dye doesn't go in, so you have catalysis outside the cell. You put them all together, what you get is this beautiful multicolored image here, where you basically have the positive nanozyme converting the pro-dye, the intracellular pro-dye to green, the sphitterion generating the extracellular pro-dye to red. You get complete selectivity. You get one system inside the cell, one fluorophore inside the cell, one fluorophore outside the cell. And this one we can do with therapeutics. So what we did is we took doxorubicin, and if you take this amine on doxorubicin, this one right here, and you allylate it, you shut down doxorubicin activity, and it becomes basically non-toxic. You put it in with the nanozyme cleaves off the allyl group, cleaves off the carbamate, and you restore the free drug. What you see is that if you take the positive nanozyme and the sphittérionic nanozyme, they both show increase in cell death as you increase concentration. So you have cell viability on the y-axis, prodrug concentration on the x-axis. As you increase the prodrug concentration, you see increasing cell death. Not surprisingly, you see better efficacy with the positive nanozyme and the sphittérionic nanozyme together, because you have two different systems, but they're about the same as the positive nanozyme. So what this is saying is it's better to convert your therapeutic into, basically your prodrug into a therapeutic, in this case, inside the cell, because the doxorubicin has to get to the nucleus. If you convert it outside the cell, it still has to get inside the cell. So works better if you do it outside the cell. If you think about a cell signaling system, however, that would be better to generate outside the cell. Okay, now, remember in the beginning, I was talking about this idea of in situ generation of chemotherapeutics using nanozymes. The idea of this is pretty straightforward. If you think about therapeutics, what you want to be able to do is you want to be able to maximize the dose of that therapeutic at the site of disease. If, for example, you're doing chemotherapy of tumors, if you can increase the dose at the tumor, then you can decrease, basically you will decrease off-target dose. You get an enhanced therapy. In other words, the more you have the tumor and the less you have the rest of the body, the more effectively you will kill the tumor with reduced off-target effects to the patient. So the idea here is, can we put the nanozyme into the tumor and then inject a prodrug systemically to basically treat the entire, to circulate through the mouse, and then have localized activation of the prodrug at the tumor. So, kind of a nice idea. We're going to do bioorthogonal catalysis with this one. In this case, we're using a palladium catalyst. A nice hydrophobic palladium catalyst goes into the monolayer of the particle, generates the catalyst, and we have a bunch of different things we can activate. We have, let's see, a green dye that can be activated. We have a near-infrared dye that can be activated, in this case through deep propargylation. And we have 5-fluorouracil, which is a widely used chemotherapeutic agent that can be deactivated through propargylation. So, how does this system work? Well, key thing is, if you're going to put a factory inside of a living organism, that factory, you want that factory to last long enough to generate therapeutics over the course of time. So one of the things we did is we took the prorotamine, the prorotamine dye, the same one that you've seen before, except this one propargylated, and we put in the nanozyme. First, we put in the nanozyme, and then we let the cell sit for 1, 2, and 3 days. And so on the right-hand side, what you see is the flow cytometry from that. And you see that the flow cytometry pretty much looks identical for day 1, day 2, and day 3, and quite a bit different than the cell only or the cell with a prorotamine. So we're getting that fluorescence. You can see that in the images up top. That cell only, prorotamine only, just the blue from the nucleus. With the catalyst in there, if you put in the prorotamine after day 1, after day 2, after day 3, you get fluorescence. You normalize the intensity from the microscopy, you see that you get pretty much the same intensity each day. So these nanozymes are stable for at least 72 hours. No degradation over 72 hours. So that's good. Okay, so the next thing we want to do is we want to put these into the tumor. So this is once again the kind of really handy tool, because ICP mass spec imaging allows us to localize the nanozyme. So what we did here is we took the nanozyme, injected it into, in this case, it's a breast tumor. And it's a breast tumor that's implanted under the fat pad of the mouse. So and this breast tumor, it's basically a 4T1 tumor. So it's a triple negative model for breast cancer. So what we can do is we can inject, then we can take the tissue, in this case, the organ, in this case, it's the tumor. We can cryosection it. In other words, slice it really thin. And then we can put it onto stages. And we can do H&E staining, which is basically the same histological staining that is used for tumor diagnosis. And then we can do ICP imaging analysis of the adjacent stain, of the adjacent slice. So here we see H&E staining of the tumor. If we look at gold, we see that we have gold localized in the tumor. You look at palladium, palladium's localized in the tumor. If we merge the two, you take red and green, you expect yellow, you see beautiful yellow, meaning everything is where it's supposed to be. Everything is localized inside the tumor. Significantly, we don't have the complete tumor filled with the nanozyme. So we're using an aggressive 4T1 model. And like I said, it's a triple negative model. We inject the nanozyme into the tumor. We wait 24 hours, and then we inject the near IR or far red pro dye. And what we see is that if we don't have the nanozyme, we don't have any fluorescence. If we have the nanozyme, we see very good fluorescence. If we take a look at the individual tissues and organs, we see that the only place we see fluorescence is in mice that have been treated with the nanozyme at the tumor. We see no fluorescence in liver, heart, spleen, lung, brain, kidney. All makes sense because that particle remains localized. So you get no uncaging without the nanozyme and uncaging only at the tumor. Now, here's what we're doing here is we've got the tumor volume. So we're looking at basically the volume of the tumor over time. And so what we're doing is you've got tumor volume on the y-axis, days on the x-axis. We're doing 5-FU, which is the 5-fluorouracil, the drug itself, the Pro-5-FU, which is the inactivated the cage drug, or PBS injection as a control. And what you see is that you get rapid tumor growth if you have the nanozyme without the Pro-5-FU. You see rapid growth with the Pro-5-FU only, and you see rapid growth with the PBS. So basically, all these controls behave the same. If you go and you take a look at either the 5FU, which is in green, you see dramatically decreased tumor growth. If you do the TTMA nanozyme plus the Pro5FU, you see basically very similar tumor growth, much slower. And if you take a look at the statistics, what you see is there also that you get quite a bit of decrease in tumor volume, average tumor weight or tumor volume with the 5FU and with our Nanozyme plus Pro5FU. So you look at that, and I'm hoping that you folks are a little disappointed, because you look at it and you say, well, you're using a really complicated system with this prodrug and this nanozyme, and you're getting the same degree of tumor growth slowing as you do with the free drug. Why not just use the free drug? And there's a really good answer for that, which is 5FU, 5-fluorouracil, is strongly hepatotoxic. In other words, it damages livers. And so if you take a look at aspartate transferase assay, this is a common assay used for liver damage. What you can see is that the controls show very normal AST levels. The 5-fluorouracil treated mice show dramatically increased AST. So they are having hepatotoxicity. That is a real challenge for the mice and would be for the patient. Whereas with the nanozyme strategy, you see no significant increase in AST. So what that means is that we are getting the full efficacy of the free drug without the off-target effects, which is exactly what we want to get from having the in situ drug factor. So with that, time's up. What I want to leave you with is that we can generate nanomaterials that have controlled interactions with proteins. These nanoparticles can be engineered to denature proteins or not denature them. If proteins denature on the surface, they create a protein coating that can be used to provide controlled activation inside the cells. What we're currently working on with this is we're working on developing anti-inflammatory strategies in macrophages to treat diseases like the acute respiratory distress syndrome, the ARDS, that's associated with COVID. Control localization of imaging agents and drugs. One of the things that we want to be able to do is increase circulation time for these nanozymes so that we can inject them systemically and have a chance to where they want to go. And then for the in situ generation of drugs at tumors, it's clinically useful to be able to inject a nanozyme into a tumor. It would be much more useful, however, if we could inject that nanozyme systemically, allow it to circulate through the body and find tumors. Then if we did that, the system would be useful for treating metastatic cancer. So with that, I'd like to thank the folks that do it. We've got a great group of students and multidisciplinary. So you look at the tools that we have here. We've got some folks here that are doing, for example, Zhenxi. He loves animal studies. So he's the one that did the animal studies for this paper. Christina loves catalysis. She did the catalysis for this work. Arohi loves doing cell work. So she did the cell work for these studies. So good team, made it all work. With that, I'd like to thank all of you for your time and attention. And I am certainly open for answering questions.
Thank you so much, Prof. Rotello. It was very interesting to learn about the different applications of the nanozymes, especially in your lab. I'm now going to do the Q&A session with you. So my first question for you is, how are the nanozymes fabricated? Are they made up of inorganic materials only?
You see, now there you got a really good question, because pretty much anything that's hydrophobic can be used to encapsulate the catalysts. So what we've done is we've done catalysis using the gold nanoparticles with the hydrophobic interior. We've done the catalysis using polymers. We've done it using nanoemulsions. Other researchers have done the same, done this sort of work with MOFs and with other inorganic substrates, surfaces. So basically, there's a wide variety of things that you can plug your catalysts into.
Okay, that's very interesting. So it doesn't necessarily, there isn't a one-step method to make it. There's many different ways to make the nanozyme, if I'm understanding what you're saying.
You are correct, and it makes it a lot of fun because, you know, if your system can be useful for delivering things into living creatures, then you can probably find a way to attach a catalyst to it.
Okay, that's very interesting. On the topic of the gold nanoparticles, I've always wondered, have you tried making it with copper or silver instead? Because I know usually if they're in the same group, do they show similar properties as the gold nanoparticles?
Okay, so basically, one of the great things about the gold nanoparticles is that they're quite a bit more stable. Copper particles will quickly oxidize, as will silver, actually. We've done some work with silver, but if you think about it, if you have a gold ring, that gold ring stays shiny all the time. You have a silver ring, it tarnishes. So that same process occurs with particles, but at a much higher rate because of higher surface area. So we'll use silver not so much as a platform, but in cases where we want to have silver in the system, for example, antimicrobials. So we can do something where the silver first acts as a catalyst, and then when the particles degraded, it becomes antimicrobial.
Okay, that's interesting. Has there ever been a thing where they usually mix metals together? So things like maybe they'll use silver with copper and rhodium, for example.
You can do that, and the thing that you'd want to have is you'd want to have a particle where those metals, where you could either do it two ways. You could do it raspberry style, where you have the individual particles and you allow them to sort of aggregate into an assembly. That would be one way to do it. Or you can do it with alloy particles. Hadn't really thought of it, but you know, for example, you could do it with something like iron palladium particles or iron platinum particles, where you would have the two metals in the core.
Okay, interesting. Okay, another question that we have from the audience. So what are the recent developments concerning biosensing nanozymes?
So that's one of the things that if you look at the nanozymes out there, there's roughly, I would say, I don't know, 4,000 or 5,000 papers a year on non-bioorthogonal nanozymes, and maybe 50 papers a year on bioorthogonal nanozymes. What the non-bioorthogonal, in other words, the normal nanozymes, they do reactions that are basically ROS activation, catalase activation sorts of reactions. And where they're really useful is they're really useful in amplification. So you think about it, you have ELISA, this enzyme, basically enzyme linked immunoabsorption assay. Oh, what is that? Well, you have an enzyme that goes and converts a substrate to a product. And that's great. Enzymes are kind of unstable and and expensive. So what people have been doing is people have been using these catalase type nanozymes to basically convert dyes, amplifying the response of the sensing system. And there's been a lot of really good work done on this, and people have developed really efficient systems that work really well under a wide variety of conditions. Not really what we do. We think about it every once in a while because we could do, of course, bioorthogonal amplification. But my students right now, I think, are much more therapeutically focused than they are sensing.
On that topic, I am curious, what other applications are there for nanozymes besides biological uses?
Okay, so if you think about it, synthetically, they're quite useful. For example, if you want to do catalysis in water, water is a great sustainable solvent for chemistry. But the catalyst, it's difficult to make a catalyst that's water soluble, an organometallic catalyst that's water soluble and stable. You can encapsulate these catalysts into polymers or nanoparticles. You have systems that not only are able to do the catalysis that you want, but they're able to be separated. So sustainable synthesis is one area that they're used. Sensing, as someone so aptly pointed out, is another area. Imaging, people are using these. They're moving into the clinic now for imaging, for example, for tumors and other diseases. So I would say those are probably the biggest areas. But as the technologies develop, people are finding new applications.
That's very cool. In terms of the using it as sensors, I was curious, how does the nanozyme leave the body after it's been injected? Does it just come out as waste? I was curious.
Okay, so basically what's going to happen is if you inject these nanozymes into a mouse, so we've done these studies and we can look at palladium, and what will happen is if we inject the nanozymes into a mouse, we'll see within a few hours, we'll see roughly half to 3/4 of the palladium injected has been excreted. And that's going to be excreted through the kidneys. And that's because the nanoparticles, basically the kidneys can excrete material up to about 5 nanometers or so. Our particles are a little bit bigger than that, but they're squishy. So a lot of them will be excreted through the kidneys. And then what will happen is you'll see a pretty rapid fall off on that. And then you'll see a long, slow drop off. And what's happening there is inside the cell, the nanozymes gradually being degraded. As it's degraded, the components are going to be exported outside the cell, and then they will be slowly, once again, excreted through the urine.
Okay. So it'll just be processed by the body normally. That's interesting to know. Another question is, what was the most interesting and intriguing challenge you observed while investigating a metalloenzyme?
Ooh, that's a really good question. I'm going to say that we are currently facing our biggest challenge, and it is an intriguing one, which is that we've been doing for about the last year or so systemic injections. And the challenge that we're facing is getting good circulation time for the nanozymes. And what we're finding is that the nanozymes are pretty rapidly getting taken up by macrophages and going to the liver and spleen. This is reticuloendothelial clearance, RES clearance. This is the bane of nanomaterials. They go to the liver and spleen because they get taken up by macrophages. So the challenge we're doing is we're working hard to figure out how to shut down macrophage uptake of these nanozymes so that we can increase their circulation time and get them targeted to the tumor. So it's really this challenge of taking something that works beautifully in cells and then figuring out how to get it to work in the animal.
Okay. So in that case, the body is doing too good of a job getting rid of the foreign invader.
Yes, it's if anybody's interested in this sort of work, it's a fun thing to look at. Is Warren Shan did a 2016 Nature Materials paper on targeted nanomaterials, where he basically found all these wonderfully targeted nanomaterials pretty much all ended up in the liver.
Oh.
So that is the challenge of nanomaterials. If you think about it, you know, that's where most of those COVID jabs you took ended up in the liver. And if we had better ways to keep them circulating, we wouldn't have to take such big jabs.
Ah, yes, also often as well. Okay, another question. Do you think of engineering custom-made proteins with higher stability rather than nanoparticles?
Ooh, that is a really nice question. And there are researchers like Stefano Menichetti that are doing beautiful work with proteins as catalysts. As a matter of fact, one of the really fun areas that people are working in is the exact same thing we're doing, but swapping metals in the metalloenzymes. So if you take, for example, swap out an iron and replace it with a platinum or palladium, you can generate a bioorthogonal enzyme instead of a nanozyme. So that's a really cool way to work, and it lets you take all the tools of biology and apply them to your system. We're trying to do that, and it's kind of working.
Okay. That's always good. That's always good. Another question, let's see. So what are the strategies to improve the efficiencies in the physiological medium?
Okay, so the basic key that we're looking at is, if you remember when we did the delivery, when we put the zwitterionic nanozymes in with the cells, they stayed outside the cell. So what we're looking to do is we're looking to take those zwitterionic nanozymes and use those to target. In other words, put things on the outside of those zwitterions that can be used to target the tumors. So we're trying to walk this tightrope because we want to slow down macrophage uptake, but we don't want to stop tumor cell uptake. So I think it's really a question of decorating the outside so that the system stays, basically doesn't get rapidly taken up by the macrophages, but can still be uptaken by the target cells. And that's where we're running into challenges, because it's not easy to balance that, because macrophages are very hungry. They're designed, they're basically the body's, I guess, garbage collectors. They're designed to go through and pick up things that are nanoparticle size, like viruses, for example. So slowing that down while still maintaining the uptake is the real challenge.
So do you find that machine learning, does it help at all with designing the nanozymes?
That's good. That's a really good question. We are just starting to work on machine learning. The challenge that you have with machine learning is that you need to have good inputs, and you need to have a lot of inputs to generate useful machine learning. So what we have to do before machine learning becomes effective is you need to basically go to, I guess you could call it, medium throughput methods. You need to be able to generate not 5 or 10 examples, because 5 or 10 examples we can plot on a graph and figure out ourselves. You need to generate 100 or 1,000 examples and test them. And then when that information gets put into machine learning, then it's going to be useful. So what we're working on is simultaneously high throughput fabrication of nanozymes and high throughput screening of nanozymes, so that we have the information to go in. And then our hope is that once we have this information, machine learning is going to be able to direct us to make new systems. And so we have a collaborator, Reed Van Lane, at University of Wisconsin-Madison, and he's been working. What he's been doing is he's been working with us, and he's been developing predictions for nanomaterials that should, for example, be efficiently taken up by cells. And so it's interesting because we have to do some back and forth, because Reed's a computational chemist, and he'll say, well, this ligand would work really good. And then we'd have to say, yeah, but that's impossible to make. So it's moving that way. And I think, like I said, if you can come up with high throughput synthesis, high throughput screening, machine learning is going to be the way to make sense of that mess.
A previous Science Cafe we actually did was on nanoparticle mega libraries. Have you ever considered using that as well for the production of the nanozymes?
Well, what we can do is we can do basically formulation strategies, and that is a little bit tricky. We haven't been able to figure out how to make a mega library. Let's see, I'm trying to think about it. We're hoping to maybe get to a kilo library.
Oh, okay, that's good enough.
Yeah, and then that's going to really be a question of figuring out basically formulation. You want to have a system where you have, a relatively limited number of synthetic systems that you can then plug like Legos into a combinatorial library.
Okay, yeah, that makes sense. Talking about finding the right system or design, have you noticed any recent trends in nanozyme design?
Well, see, on the nanozyme, I think there's been some pretty interesting work being done on what's called single site catalysis, where you basically have systems where you put in individual metal atoms that can catalyze reactions. Those work really well, for example, on systems like a moth or other inorganic systems. There's been some really interesting work on developing new bioorthogonal catalytic reactions. So one of the systems that I think Meggers developed was a really nice iron porphyrin-based activation. Beauty of that is iron porphyrin you can use, for example, hemin, a naturally occurring porphyrin, to do catalysis, meaning, you don't have to worry about the excretion of that metal or that catalyst. It's just natural. So I think that's another area that's nice, is this idea of using chemistry that's more, let's say, more benign.
Okay, yeah. On the topic of natural enzymes, would nanozyme efficiency be much lower than that of natural enzymes?
I'm going to say that the inorganic nanozymes that people have made can be actually more active than the enzymes. I'm not sure exactly if they're more active on a per atom basis, but they're certainly really highly active. For our system, what we find is that with our bioorthogonal chemistry, we're getting, I guess you would call it, moderate rate enzyme activity. We're not getting, like the super carbanic anhydrase sort of incredibly fast reaction, but we're getting reactions that are consistent in a per catalyst basis with a decent number of enzymes. And there's room for improvement on that, because obviously the more efficient the catalyst is, the faster it's going to be able to convert substrate, and the less you'll need of it.
That makes sense. So with time being on our tail, the last question will be, what is your favorite natural enzyme, and which one has inspired most of your work?
Oh, geez, my favorite natural enzyme. I'm going to say my favorite natural enzyme is chymotrypsin. And chymotrypsin is my favorite at the beginning because it was the first enzyme where somebody explained how it worked. And I thought it was so amazing how you had that thiol and you had the imidazole, and how you're able to transfer those protons all around. That was really cool. And then that I guess initial love I had, this was back, probably 84 or so, that initial love came back in the early 2000s, where we used chymotrypsin as a model enzyme to bind our nanoparticles to. So the chymotrypsin was the one where we showed that, we can bind to the chymotrypsin, we can denature it. We showed that we can denature chymotrypsin, bind our particle to it, and renature it. So we had a lot of fun with chymotrypsin. So that was my favorite one. We're not using it right now, but we might.
That's very interesting. Thank you so much. Thank you so much, Prof. Rotello. We will now move on to the closing, but thank you again for all answering our questions and accepting our invitation.
Thank
I will now pass it on to Wally. Thank you.
Thanks again, Professor Vincent, for giving this amazing presentation, and also for answering all the attendees and all the audience questions. It was pretty much amazing, and hopefully, I hope for you good and amazing work in the future. So moving ahead with our schedule. So as you know, the IYCN Science Café is a series that has began from 2022, beginning with July. You can find all the series on our YouTube channel through this link, bit.ly/IYCN_Science Café, where you can find all the previous recording. Also, this is a statement for our commitment to equity, diversity, and inclusion. As a network, we are welcoming all people from all nationalities from all the world with no discrimination. And we are also trying our best to bridge international collaborations with each other. Finally, I would like to thank our speaker again, Professor Vincent, for accepting our invitation to give this amazing talk. And also, I would like to thank all the audience for all their attention, and have the rest of the day. Have nice rest of the day, and hopefully we'll meet soon. Thank you.